In this lecture, I'm going to talk about encryption, something very popular at the moment, but something that's been around for years and years and years, but only since the advent of computing has it become really useful. So the process of converting information or data into code, especially to prevent unauthorized access. We've heard it again and again. My phone is encrypted, my emails are encrypted, the encryption was broken. So there's a couple of kinds of encryption. Symmetric key encryption are algorithms for which cryptography that use the same cryptographic key for both encryption of plain text and decryption to cipher text. So that means that actually, if you know how to encrypt, you know how to decrypt, so you know everything. What's become more prominent in the past while is asymmetric cryptography, public key. Anyone can have the key that encrypts, but that doesn't tell you how to decrypt. So I can give my encryption key to anyone in the world. They can encrypt a message, send it to me, but I am the only person in the world who can translate it. The best way of thinking this is, if I have a box and there's a lock in the box, if I have a key and I send it to my friend and they also have a key, that's symmetric. Everyone has a key to the box. So if you copy the key, anyone can open it. Now, asymmetric is, I send the box to my friend, open. My friend puts the message in the box, they close it and it locks and sends it back to me, and only I have the key. Yeah, that's the difference between symmetric and asymmetric. Asymmetric is far more private, far more harder to break. So we're going to talk about the two easiest ones, the Ceasar cipher and the McNary cipher, both named after people. We also have to do a situation where, because we're dealing with letters, we translate them to numbers. So A becomes 0, B 1, and so forth, and Z to 25. But we also have to work in mod 25 because we have to add letters together. So if you have the letter F and you add the letter Z to it, or Y, we'll say, what is Z plus Y, or X plus Y, or whatever? And that's why we have to use mod 26. So if you add together number 23 and 7, gives you 30. There's not 30 letters in the alphabet. So what do? You have to go round. And that's where a modular arithmetic is so important. So, for example, mod of 0 is 0. Mod 26 is 0, 0. Mod of 3 plus 3 is 6. That's fine. 26 mod 6. So this is a special one. If you're at the 26th letter, you go back to A. Minus 3 mod 26. You can't have minus numbers, but what is minus 3? So you count backwards. 0 was A, minus 1 is Z, minus 25, minus 24, minus 23. So that's 26 minus 3 gives you the mod. Lastly, 23 plus 7, that is 30. There aren't 30 letters, so what you go 30 minus 26 gives me 4. So you end up here, E. So Julius Gaius Caesar, around 700 BC, was a Roman general who would then later become the dictator for life of Rome. But one thing Caesar was good at, except for killing people, was promotion. And when he was in France, it's called the Gallic Wars, he would write letters back to Rome about how great he was, how the war was going, and he would encrypt them. He'd also encrypt messages to his other generals and the legions. And that's where it comes from. That's the legend that Caesar comes from, the Ceasar cipher. So he wished to send messages without the enemy knowing what he was doing. This kind of contradicted the narrative that Caesar was fighting barbarians. Barbarians can read. So therefore are they barbarians? No, they're just people that he was committing genocide upon. So what would happen would be, he'd translate the word Caesar into ZXBPXO and send that to Rome, and they would translate it back. How would he do it? Very easily. He would say, this was the original text, the letters A to Z, and it'd be different alphabet for Latin. And then he'd map them, said A goes to Z, X, B goes to Y, C goes to Z, D, B, and so forth. So you have this. So you have your plain text, and then you have your cipher. Yeah. So instead, we deal with numbers. So what do we have for the formula? To encrypt a word or a letter, you take each letter and you move it back 3 places in this example. So in that example, as I say, D goes to A. But if you see a D, what does that translate to? A. Yeah. So that's how deciphering go. So to encrypt, you shift it back 3 letters. To decrypt, you shift it forward. And the only area that you have to be careful about is with the overlap here. Yeah, you have to know that it's a wraparound. It goes A, B, C, D, E, F, G, H, I, J, K, L, M, P, Q, R, S, T, U, V, W, X, Y, Z, A, B, C. Yeah. So here we have, I always write down A is 0. I always write down the alphabet myself when I'm doing this. It just minimizes error. So I want to translate the name Ceasar into encryption. So C, and I'm going to use the encryption of -3. The letter C is 2. I subtract 3. That gives me -1. 25. That gives me the letter Z. Yeah. A, -3. So A is 0. -3. Well, that becomes 26. So that's X. E, which is 4. -3, which is 1, gives me B. S -3. S is 18. -3 gives me 15. So that gives me P. A is 0. -3 gives me X. Or -3. That gives me 14, which is O. So Ceasar becomes ZXBPXO. And then I want to decrypt, starting with Z. So Z plus 3, that's 25 plus 3 is equal to 2, which is C. X plus 3, 23 plus X is 26, which is 0, A. B plus 3 is 1 plus 3, which is 4, which is E. P plus 3 is 15 plus 3, which is 18, which is S. X plus 3, which is 23 plus 3. Oh, and that should be 0. Which is A. And lastly, 17 O plus 3, which is 14 plus 3, which is 17, which is OR. So Ceasar. So we've gone from Ceasar to Zibidpublics back to Ceasar. Encrypt, decrypt. So that was a very specific case of Ceasar where we subtracted 3. But what's the general formula of Ceasar? General formula is you add, you shift the letters by n. Now n could be plus or minus. N can actually only be between -26 and +26. And to decrypt, you do the opposite. Yeah, and that's it. Those 2 formulas, encrypt and decrypt. So in encryption, we start off at I is equal to 0. We have our list of letters, and we just loop our way through the formula. So it's just a for loop. Ceasar encryption for I in range of length 0 to length x. yi, which is the encrypted message, is equal to xi plus n 26. And n will change every time. Or change, well, you have to tell the person what n is to make sure they can decrypt. Similarly, to decrypt, I is equal to 0, y, you run your way through to get the decrypted form, and it returns x, and it loops its way through the whole letter, the word. Similarly here. Yeah. And so the only thing you need to encrypt or decrypt is n. You just have to know how far the shift is. So here we have our encryption, and decryption flowchart in maths and in pseudocode. So here we have how an engineer would think about it, how a mathematician would think about it, and then how a computer scientist would think about it. So I'm just going to go through a couple of examples for n is equal to 4. So for the Ceasar cipher as n is equal to 4, what it is it shifts everything by 4. Very straightforward. So Ceasar, which is C, adds 4. So C becomes G. A, which is 0, you add 4, which is 4, becomes E. E, which is 4, add 4 becomes I. S, add 4. S is 18, plus 4 is W. A plus 4 is E. Or plus 4, 17 plus 4 is 21, which is V. And then to go backwards, you subtract. So G minus 4, 6 minus 4 is 2, which is C. E minus 4 is 0. I minus 4, 8 minus 4 is 4, is E. W minus 4, which is 22 minus 4, which is 18, which is S. E minus 4, which is 4 minus 4, which is A. And lastly, 21 minus 4, which is 17, which is OR, Ceasar. So that's just a 4 shift. Yeah. What about a 20-letter shift? So this is as straightforward. But the reason why I wanted to do this one is just it emphasizes that wraparound function. So C is 2. 2 plus 20 is 22. That's W. It doesn't wrap around. A stays, just adds 20, which is U. E, add 4, gets to Y. M, now 18 plus 20 is 36. 38, I mean. 38 minus 26 gives me 12. And that gets me my M. That's our wraparound nature of the function. Then once again with A, we go directly to U, and OR is 17 plus 20. 17 plus 20 is 37. 37 minus 26 is 11, and that's where we get the L. Yeah. And decryption is the opposite way. So 22 minus 20 is 2, that's C, that's easy enough. 20 minus 20 is 0, which is A. 24 minus 20 is 4, which is E. M, 12 minus 20 is minus 8. 26 minus 8 is 18, and that gets our S, our wraparound the other way. 20 minus 20 is 0, which is A. And lastly, 11 minus 20, minus 9. 26 minus 9 is 17, and that's where our OR comes from. Just to think about the wraparound nature of it. And we can even include a minus N. So it just means that 2 minus 6 is minus 4. That's 22. That gets mapped to W. A minus 6, which is 20, which is minus 6, which is 26, minus 6, which is 20, which is U. E, which is 4, minus 6 is 24, because that's 26 minus 2. S, which is 18, minus 6, 12, that's easy enough. A is U again, OR is L. So to decrypt, N minus 1, so that's minus minus. So W plus 6, 22 plus 6, wraps us back around to C. U, which is 20, 20 plus 6, which is 26, which is 0, which is A. Y, which is 24, 24 plus 6 is 30, minus 26, which is 4. 12 plus 6 is 18. 20 plus 6, once again, is A. And L plus 6 is 17, which is OR. So once again, does it matter if it's plus or minus? No, as long as you know your modular arithmetic, which you've done some before, it all falls into place. Now, how do you break a Ceasar cipher? And why do people not use it anymore? Well, one very brute force way is you find a word you know. For example, Caesar would always sign Caesar, or Julius Augustus maybe. And you just go, how many different ways can I encrypt Caesar? And here's every single shift possible for Caesar. Yeah. So if you're given this, can you decrypt it? You just work your way through it. And then if one of them turns out to be a word you know, then you know what letter shift it is. Yeah. You try every shift and it'll come out. Now, this could be quite laborious, but it's not impossible. You know, there are only 26 possible shifts. So it's doable, very doable. Another thing, which is easy enough to do, you count the letters. So the most common letter in the English alphabet is E. Yeah. So if you have a long enough text and you go through the text and find out what letter is common in the enciphered text, then you say that will be E, and immediately you've solved the answer. You can reverse engineer the answer from there. So therefore, the advent of computers, which can do this kind of work very quickly because it's quite simple, means that the Ceasar cipher is useless.